You've typed in a shared Google Doc with 4 other people at the same time. Nobody's cursor jumps, nobody's sentence gets eaten. You type, they type, and the page just works. To you, that's boring. To the computer, it's a nightmare. 4 machines, 4 different networks, 4 different amounts of lag, all editing the same string of characters at the same instant, with no way to know what anyone else just did. So here's the real question. How do you keep a document consistent across machines that can't agree on what right now even means, without locking the file every time someone hits a key? The answer is a data structure with a genuinely elegant piece of math behind it, the CRDT, short for conflict-free replicated data type. Today we're taking one apart to see exactly how it makes simultaneous editing not just possible, but guaranteed to never break. To see why this is hard, forget Google Docs for a second and picture the simplest possible shared document. 3 letters, C-A-T. Alice and Bob both have it open. Both see cat. Alice wants to turn it into chat, so her editor sends an instruction. Insert H at position 1. At almost the same instant, Bob wants cats, so his editor sends insert S at position 3. Both instructions were calculated against the same document, the cat they were both looking at when they typed. Now those 2 instructions land on a server, and the server has to apply them in some order. Say Alice's goes first. Insert H at position 1. The document is now chat. Fine, except every letter after that H just slid 1 spot to the right. The T used to be at position 2. Now it's at position 3. Then Bob's instruction runs. Insert S at position 3. Bob picked 3 while looking at cat, where position 3 meant after the T. But the document isn't cat anymore, it's chat, and position 3 now points at the T itself. So the server inserts S right in front of it. The result, C-H-A-S-T. Not chat, not cats, chast. Both instructions were followed exactly, in a perfectly reasonable order, and the document still came out wrong. That's because position 3 in cat and position 3 in chat are 2 different places. A position number is only meaningful for the exact snapshot it was measured against, and the snapshot moved. Now add deletion to the mix, and it gets worse. Say Alice deletes the A at position 1. The document shrinks to CT. If Bob's insert instruction, put an S at position 3, arrives after that, position 3 doesn't exist anymore. Depending on the system, that either crashes or silently drops the character somewhere nobody intended. Same root cause every time. A position number is not a stable address. It's a description of where something used to be, and it goes stale the moment anyone else edits the document. Historically, there were 2 ways around this. The first is the blunt one, pessimistic locking. While Alice is typing, the file is locked, and Bob's keyboard effectively does nothing. It solves the conflict by not allowing one to exist, at the cost of exactly the collaborative feel you'd want from a collaborative editor. The approach Google Docs made famous is smarter. Operational transformation, or OT. Every instruction goes through a central server first. The server looks at what else has happened since that instruction was created, mathematically rewrites the position numbers to account for it, and only then applies and broadcasts the result. It's the same insert and delete instructions from before, just corrected in flight before they can collide. OT works, and it's shipped in production for a long time, but it's genuinely hard to get right, and it leans on that central server as the single authority reconciling everyone's edits, which means offline editing is awkward. You can't cleanly merge a batch of changes made with no server in the loop, because there was nothing there to do the transforming. CRDTs take a completely different angle on the same problem. Instead of fixing up operations after the fact, they change what a position is in the first place, so that 2 conflicting edits become mathematically incapable of stepping on each other. The guarantee CRDTs they're built on rests on 3 properties: commutativity, associativity, and idempotence. Strip the jargon and it says one thing. No matter what order edits arrive in, and no matter how many times one gets replayed, every machine converges on the exact same final document. No central referee required.
Here's how a real CRDT, the kind used in local-first collaborative editors, pulls that off. Every single character gets a unique permanent ID the moment it's typed. which client typed it, plus a counter that ticks up for every edit that client makes. Not a position, an identity. Back to CAT, all typed by Alice. C becomes Alice 1, A becomes Alice 2, T becomes Alice 3. Those names never change, no matter what gets inserted or deleted around them later. IDs alone don't tell you the order though, so each character also remembers its two neighbors at the moment it was typed, the character to its left and the character to its right. Call them origin and origin right. C was typed first, so its left is nothing and its right is the empty document. A came right after C, so its left is C. T came after A, so its left is A. What you end up with is a tiny linked list. C points to A points to T, anchored by identity, not by counting characters from the start. Now Alice wants an H between C and A. Her editor doesn't ask for position 1. It creates a new character with origin C and origin right A. That's a coordinate built out of two permanent names, and nothing that happens anywhere else in the document can invalidate it. Here's the interesting part. Say Bob, on a different machine, at almost the same moment, independently decides to insert an H in that exact same gap. Same origin C, same origin right A. Both machines now have two brand new characters claiming the same slot. This is where the client ID earns its keep. The rule is simple and fixed in advance. When two characters share the same origin, the same left neighbor at the moment they were created, sort them by client ID. Alice comes before Bob alphabetically, so on every machine, without any of them talking to a server, the result lands in the same order. C, then Alice's H, then Bob's H, then A, then T. Not because someone adjudicated it, because every machine ran the same deterministic rule on the same data and got the same answer. Because every character carries a permanent ID and two permanent neighbor references, it no longer matters when an edit shows up. If Alice's insert is delayed 3 days by a flaky connection, it still knows exactly where to go, the gap between C and A. And if Bob's already sitting there, the same client ID rule breaks the tie, every time, on every machine, regardless of arrival order. Deletion still needs handling, though. If a character is fully erased from the structure and some other, still in-flight edit was anchored to it as an origin, that anchor now points at nothing. CRDTs solve this with Tombstones. Hitting backspace doesn't remove the character from the underlying structure, it just flips a deleted flag on that character's permanent ID. The screen hides it, so visually it's gone. But the identity is still there, still available as an anchor. If a delayed edit references that ID as its origin, it finds the tombstone, slots in right next to it, and the document stays perfectly consistent, even though the character it's anchored to hasn't been visible on anyone's screen for hours. Because consistency here is guaranteed by math instead of by a server being reachable, CRDTs unlock something bigger: local first software. Get on a plane, edit for 10 hours with zero connection, make thousands of changes, and the second you're back on Wi-Fi, your copy merges into everyone else's with no conflict dialog and no frozen screen. Because every character you touched already carried the identity and neighbor references needed to slot back in correctly. None of this is free, of course. A permanent ID and 2 neighbor references per character would balloon a long document's memory footprint if stored naively. Production CRDT libraries compress and index this aggressively, layering a balanced tree index on top of the underlying linked list, and periodically garbage collecting old tombstones. So real documents don't grow without bound just from accumulating history. Strip it all the way down, and the shift is this. Instead of a fragile system where a position's meaning depends on everything that happened before it, you get an immutable, mathematically sound timeline of who did what in what order, one that any machine can replay and land on the identical answer. That's how CRDTs solve collaborative editing.